When we look at an airplane taking off, we're seeing a masterclass in engineering. But the same is true for a skyscraper resisting the wind, a satellite holding orbit, or the electrical grid powering a city. These entirely different technologies rely on a shared mathematical foundation known as Euler's equation. However, a quick search reveals that Euler's equation isn't a single formula. It's a family of completely different math governing fluids, solid structures, physical motion, and invisible signals. This is the work of Leonhard Euler, an 18th century mathematician who was so prolific that his name became the standard for the foundational rules of entirely separate scientific fields. Euler established the formal language for these domains, defining the rules that bridge abstract calculations with the behavior of the physical world. Consider the first of these pillars, fluids. In the real world, air and water are sticky. They generate friction and chaotic drag as they move. Euler bypassed this complexity by proposing a theoretical model called inviscid flow, which treats a fluid as if it has absolutely zero viscosity or friction. While a frictionless fluid is physically impossible, this math is highly accurate for aerodynamics. It's used today to calculate the lift of thin airplane wings by focusing on pressure rather than the stickiness of the air. These exact same foundational equations also explain how invisible energy moves through the water, particularly within massive rolling ocean swells. This diagram shows what's happening inside the swell. The water isn't a moving wall. Instead, Euler's math shows individual particles traveling in slow, open circular loops as the wave passes through them. By mathematically removing friction, Euler provided a solvable framework for flight and ocean tides that remains an engineering standard today. Moving from fluids to solid objects, we enter the world of objects spinning in three-dimensional space. Euler's rotational equations map how an object spins around its three principal axes of inertia: length, width, and depth. These equations predict the tennis racket effect. Spun along its middle axis, the object suddenly twists and flips in an unstable, chaotic way. This isn't just a party trick. It is the exact math used to predict and control the tumbling behavior of satellites in the vacuum of orbit. Euler's work here exposes the specific, sometimes chaotic rules that govern the movement of every solid object in the universe. On the ground, the narrative shifts to stationary structures holding up immense weight. Euler discovered that slender structural columns don't usually fail by crushing straight down. Instead, they fail by bowing outward laterally, a phenomenon known as buckling. Here, boundary conditions matter. A column pinned at its ends bows easily. But a column rigidly fixed at both ends resists bending. By fixing those ends, the math proves the column supports 4 times the load before buckling. Engineers used this formula to design the structural frame of the Willis Tower. It allows for slender columns that maximize interior floor space while ensuring stability under massive weight. Euler's formula is why we can construct slender megastructures without them collapsing outward under pressure. Finally, we move into the invisible world of energy and Euler's formula, notated as e to the power of j theta. This formula links exponential growth with cyclical waves by taking a signal and wrapping it into a circle on a 2D complex plane. Electrical engineers rely on this relationship to manage the high-voltage transmission lines that make up the power grid. These massively long transmission lines create phase shifts that make power delivery inefficient. By using Euler's math, engineers install capacitor banks at substations to match impedance and keep electricity flowing smoothly. Euler's formula provides the link engineers need to convert invisible waves into the stable, reliable power that runs the modern world. We are looking at 4 totally different physical domains, each governed by their own variables, yet all decoded by the same mind. Euler's genius was his ability to strip away the messy noise of the physical world to find the pure, calculable structural skeleton underneath. Every time we board a flight, enter a high-rise, or turn on a light bulb, we are living in a world built on the foundations Euler laid 3 centuries ago.